All right, let's jump right into it. In physics, every single measurement has to have a unit. And when those numbers get extreme, we use prefixes. You probably know that a kilo means you multiply by 1,000, but a micro means it's incredibly small. So to convert something like 5 micrometers into meters, you wouldn't multiply it, you need a smaller number of meters, right? So you divide by 1,000,000. You can also write this in standard form as 5 times 10 to the minus 6. Now, alongside units, the absolute most fundamental concept we measure is energy, specifically in joules. But energy isn't a physical object you can hold in your hand, it's a conserved quantity. That means it absolutely cannot be created or destroyed, it can only be shifted around.
Section 1. Energy stores and resources. So, rather than saying types of energy, we talk about energy shifting between specific stores. When objects interact in a system, energy simply transfers from one store to another. And in a perfectly closed system, no energy is lost to the surroundings, and none comes in. The total energy stays exactly the same, it just changes form.
Okay, there are 5 core formulas you need to calculate these stores, so let's rattle through them. Kinetic energy is 1/2 times mass times velocity squared. Basically, go faster, get more kinetic energy. Gravitational potential energy, or GPE, is mass times gravity times height. Elastic potential is 1/2 times the spring constant times extension squared. For thermal energy, it's mass times C times the change in temperature. And that C is crucial. It stands for specific heat capacity, which is just the energy needed to raise 1 kilogram of a substance by 1 degree Celsius. Finally, power. Power isn't actually a store, it's a rate. It's simply the energy transferred divided by time, and we measure that in watts, which are really just joules per second.
Now here is a massive time-saving shortcut for falling objects. Because energy is conserved in a closed system, if an object falls, all of its GPE turns directly into kinetic energy. So we can literally equate the two. mgh equals half mv squared. Notice how the mass m is on both sides. That means it cancels out entirely. You just rearrange it to get v equals the square root of 2gh. The incredibly cool takeaway here is that an object's mass doesn't matter at all when calculating its final speed from a drop. You only need the height. Of course, the real world isn't a perfectly closed system. Energy gets wasted all the time, usually as heat. Efficiency is simply the useful power out divided by the total power in. We test this practically by wrapping cans in different types of insulation just to see what retains heat best. But where does our initial energy actually come from? Well, energy resources. We harness energy to turn generators using finite sources like coal, oil, gas, and nuclear fuel, which inevitably will run out. Or we use renewable sources that won't run out like wind, solar, geothermal, and biofuels.
Moving on to Section 2, electricity and circuits. Electricity is essentially just the flow of charge, and those charges are carried by tiny little electrons. Just a quick note, by convention, we always say current flows from the positive terminal to the negative terminal of a battery, even though the actual electrons flow the other way.
To really map out circuits, we have to rely on some core electricity math. Because individual electrons are just so tiny, we group them into batches called coulombs. Current, I, is just the rate of flow of these coulombs, so charge Q equals current times time. Next up, potential difference, or voltage. This tells us the energy transferred per coulomb. We measure it by placing a voltmeter in parallel across a component to literally see the energy drop. Then we have Ohm's law, V equals I times R, which beautifully links voltage, current, and resistance. And for power in circuits, it's either P equals V times I, or if we substitute Ohm's law in there, power equals I squared R.
You have to remember there are completely opposite rules for series and parallel circuits. In a simple single-loop series circuit, the total potential difference is shared among the components. The current is exactly the same everywhere, and you simply add the resistors together to get your total resistance. But in a parallel circuit with multiple branches, the potential difference is the same across every single branch, and the current actually splits and is shared. And here is the real kicker. Adding more resistors in parallel actually decreases the total resistance. Why? Because you're giving the current alternative routes to flow through.
It's really important to notice how different components behave when you graph their current against voltage. A standard resistor gives a perfectly straight line. It's ohmic, meaning its resistance stays completely constant. And here's a classic exam board trick to watch out for. True resistors maintain constant resistance even when heated. But a filament lamp is not ohmic. Its line curves because as current flows, the metal ions vibrate more, they heat up, and that increases the resistance. We also have diodes that only let current flow in one direction, thermistors where resistance actually drops as temperature rises, and LDRs where resistance drops as the light gets brighter.
Let's look at where this electricity actually comes from.
Batteries provide direct current, or DC, which constantly flows in one single direction. But the mains electricity plugging into your house, that's alternating current, AC. It rapidly goes back and forth at a frequency of 50 Hz, averaging out to 230 volts. Inside your plug, the brown live wire carries this alternating potential, the blue neutral wire stays at 0 volts, and the green and yellow earth wire is purely there for safety. If a fault suddenly makes a metal appliance casing live, that earth wire directs the current safely down to the ground, and that sudden spike in current blows the fuse, instantly cutting the power.
Now, before that electricity ever hits your plug, it travels through the national grid. And the logic here is absolutely brilliant. Power stations generate massive currents. If that went straight into transmission cables, the resistance would turn all that energy into wasted heat. So they use a step-up transformer to massively increase the voltage. Because power equals voltage times current, increasing the voltage means the current drastically drops. This super low current travels efficiently through the cables across the country. And then a step-down transformer lowers the voltage back to a much safer 230 volts for your home.
But electricity is not always neatly flowing in wires. When you rub insulating materials together, friction physically strips negatively charged electrons off one object and dumps them onto another. The object losing those electrons becomes positively charged. As always, opposites attract and likes repel. This charge creates an invisible electric field around the object. Field lines always point from positive to negative. Around a charged sphere, the field is radial, spreading outward in all directions. But if you have two oppositely charged parallel plates, the field lines are perfectly straight and parallel, creating a uniform electric field where the strength is exactly the same everywhere. Section 3. Density and states of matter. So density is really simply a measure of how compact the mass is within an object. The formula is straightforward. Density equals mass divided by volume. Finding the density of a neat, perfectly square block is easy with a ruler and a balance. But what if you have an irregular shape, like, say, a chess piece? You can't calculate its volume with a ruler. For an irregular shape, we use the Archimedes method. First, you get the exact mass on a balance. Then, you gently lower the object into a Eureka can that's filled to the very brim with water. The object will displace a volume of water that is exactly equal to its own volume. You catch that displaced water in a measuring cylinder, read the volume, and finally just divide the mass by that volume to find your density.
Now, whether that chess piece is solid, liquid, or gas depends entirely on the behavior of its particles. You need to drill this exact definition into your mind. Internal energy is the total sum of the kinetic energy and potential energy of all the particles within a substance. And the golden rule here, the thing you can't forget, is that only kinetic energy or potential energy can change at any one time. Never, ever both simultaneously.
Let's break that down. When you heat a block of ice, its temperature rises. The particles vibrate faster and faster, meaning their kinetic energy is increasing. You calculate this using the specific heat capacity equation. But the exact moment it hits 0 degrees and actually starts melting, the temperature plateaus. It just stays constant. The thermal energy you're adding is no longer speeding up the particles. It's being used to physically break the bonds between them. This increases their potential energy, causing a state change. For this specific process, we use E equals mass times specific latent heat.
Once a substance finally becomes a gas, those particles are free. They're moving fast and entirely randomly. Gas pressure is simply the result of those particles colliding with the walls of their container. If you heat a gas, the particles gain kinetic energy. They move faster, and they hit the walls much more frequently and with far greater force, driving up the pressure. You can also increase pressure by compressing the gas, say, halving its volume. Because, at a constant temperature, pressure and volume are inversely proportional. If you have the volume, the pressure doubles. That is P1V1 equals P2V2.
Section 4. Atoms, isotopes, and radiation. What are those particles actually made of? Let's dive into the very building blocks of matter and look at what happens when their cores become unstable. Our understanding of the atom evolved surprisingly fast. First, J.J. Thomson discovered electrons and proposed the plum pudding model. Picture a blob of positive charge with negative electrons just dotted throughout it. Then, Ernest Rutherford's gold foil experiments proved that the positive charge wasn't a big blob at all, but was actually concentrated in a tiny, dense nucleus right at the center. Niels Bohr later realized that electrons orbit this nucleus in very specific shells. And finally, James Chadwick discovered that the nucleus also contains neutral particles, which he aptly named neutrons.
When you look at any element on the periodic table, you're looking at atomic math. The bottom number is the atomic number, which is just the number of protons. And this is absolutely crucial. The number of protons solely defines what the element is. change the protons, you change the element. The top number is the mass number, the total of protons plus neutrons. But you can actually have versions of the exact same element with extra neutrons. We call these isotopes. For example, carbon usually has a mass of 12, but add 2 extra neutrons, and you've got the heavier isotope, carbon-14.
Now, if a nucleus has too many neutrons, it becomes unstable. It wants to be stable, so it decays, literally emitting radiation to get there. There are 3 main types. Alpha radiation is a heavy little bundle of 2 protons and 2 neutrons. Because it's so massive, it has incredibly high ionizing power. It just knocks electrons off everything in its path, but it's easily stopped by a single sheet of paper. Beta radiation is a super fast-moving electron ejected when a neutron turns into a proton. It's moderately ionizing and can be stopped by aluminium. Finally, gamma. Gamma is an electromagnetic wave emitted by the nucleus. It has very low ionizing power but massive penetrating power, really only reduced by thick lead or concrete.
Radioactivity is simply the rate at which these sources decay, and we measure that in becquerels. Over time, as more and more nuclei decay, the overall activity drops. We measure this drop using a concept called half-life. Look closely at this definition. It is the specific time it takes for the activity to halve. Now, a very quick warning for your exams. If an activity drops from, say, 96 to 12, do not just divide 96 by 12. That's a trap. You have to literally count the halvings. 96 halves to 48, 48 halves to 24, and 24 halves to 12. That is 3 distinct half-lives. You use the total time given to figure out the length of one single half-life.
Section 5. Nuclear fission and fusion. Let's scale things up quite a bit from natural decay to intentionally splitting and joining atoms.
There is a really stark contrast between earthly reactors and the stars in the sky. Induced fission happens when we purposefully fire a slow-moving neutron at a very heavy nucleus, like uranium. The nucleus absorbs it, becomes wildly unstable, and violently splits in 2, releasing immense thermal energy and 2 or 3 more neutrons. Those new neutrons go on to split more atoms, creating a chain reaction. Nuclear reactors carefully control this exact chain reaction to generate electricity. Fusion is the exact opposite. 2 highly energetic, very light nuclei, like hydrogen, are literally forced to join into a heavier one, like helium. This requires incredible temperatures and massive pressures to overcome the natural repulsion between the nuclei, which is exactly what's happening right now in the core of our sun.
But here is the most provocative physics concept of all to end our review on. Whether you're splitting atoms apart in fission or crushing them together in fusion, huge amounts of energy are released. But how? Well, because in both of these reactions, the total mass of the products at the very end is actually slightly less than the mass you started with. That missing mass didn't just vanish into thin air. It literally transformed into pure energy. It is the ultimate manifestation of the idea that mass and energy are perfectly interchangeable. So think about this. If just a tiny fraction of a percent of missing mass can power the entire sun or level a city, what other incredible energy is currently locked away inside the matter all around us?